Buenos días, estudiantes. Hoy es miércoles 1 de abril y bienvenidos a esta lección de AP Español, Lengua y Cultura. De nuevo, yo me llamo Miguel Ferba y seré el profesor de esta lección hoy. Y bienvenidos a algunos participantes nuevos que tal vez estén aquí por la primera vez. Okay, in case you haven't checked your calendar, today is April 1st, and many of you watching now probably know what that means. That introduction was nothing more than a silly April Fool's joke. Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Faribaugh, and I really do teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. This is day 6 of our series of lessons on AP Chemistry. These virtual lessons we presented daily, Monday through Friday. We began on Wednesday, March 25th, and this series of lessons will run through Friday, May 1st. Today and tomorrow will be a review of the chemistry in Unit 2. That would be molecular and ionic compound structure and properties. I would like to remind you, as always, that you should feel free to pause this video if you feel that I'm going too fast, or if perhaps I'm not even speaking English, or if you need more time to think about a question that I've asked you. Again, for more information on the AP exams, you can visit the following website. That's apcentral.collegeboard.org. And you can get updates of the AP exams. All right, well, if you have a pencil or a pen and say to 3D10, but you don't have to necessarily write the entire configuration full like that. You could also abbreviate it with the noble gas, argon, and then write 4s2 3D10. So either of those would be acceptable. And the language of the AP question, unless they say specifically write the complete configuration, and they make any comment about not using the noble gas abbreviation, either of these would be acceptable. All right, well, then the next part of the question had to do with which sublevel are you going to remove electrons from when zinc becomes oxidized? So zinc normally loses 2 electrons. So here is the rule. When removing electrons from a neutral atom to form a positive ion, the electrons in the orbitals that have the highest energy level are removed first. So if you have a choice between 3D and 4s, which electrons should be removed first? And the answer is 4s. You should definitely remove the electrons from the 4s sublevel. So therefore, in this case, if you have a choice between 3D and 4s, you go with the highest energy level. So this is the scoring guidelines, the official answer. All right, let's move on to the next part of the question. This question has to do with iron. We have to compare iron 2+ and 3+, and we need to also talk about electron configuration. Oh, okay, that's what happened. I was trying to figure out exactly why. Sorry about that. I was trying to figure out why my camera went off. I think it's back. All right, let me just continue here. I just didn't see my camera. Okay, so here we are talking about the ground state electron configuration of the iron 2+ ion. Now, the ground state electron configuration of iron is going to be 1s2, 2s2 like we did before, all the way up through 3d6. But you have to be careful that you read this question carefully. Okay, in this case, we're not looking at the electron configuration of iron, the atom. we're looking at the electron configuration of the ion, the +2 ion. So you have to be careful that you realize that we are answering the correct question. This is not going all the way through to this particular configuration. We're stopping by removing the 4s. So the configuration of the iron 2+ ion would be without that 4s. All right, and then our next part of the question, so we answered the first part, which is the electron configuration of iron 2+. The next part of the question says that the radii of the ions, iron 2+ and 3+, are given, and we have to explain why is iron 2+ larger than iron 3+. Now, before I talk about this particular question, let me just remind you of something that Mr. Byrne talked about yesterday. So this would be, for example, in a period on the periodic table, the atomic radius is getting smaller within a period from left to right. And we normally describe this because of increasing nuclear charge. So the problem with that particular trend is it doesn't apply in this particular case. We're not comparing sodium with magnesium. We're not comparing fluorine with neon. We're comparing iron with iron. So in fact, because each of them has the same number of electrons, because each of them has the same number of protons and they have a different number of electrons, they have the same nuclear charge. So if we're going to compare the radii of iron 2+ and iron 3+, we cannot say that iron 3+ has more protons or greater nuclear charge. All right, well, before we answer this question, let me remind you of an example from another part of the periodic table. So why is fluorine -1 larger in size than the fluorine atom? And the answer is because fluorine, the -1 ion, the fluoride ion, has one more electron. So it's not about protons, it's about more electrons. So why is it larger? It's because of electron-electron repulsions. So therefore, that is what we're going for in this question. Each ion, iron 2+ and iron 3+, have the same number of protons, but with one more electron. That's going to cause the iron 2+ to be larger, and you should mention electron-electron repulsions, so any student's answer that talks about greater nuclear charge is not going to receive credit for this question. All right, then the last part has to do with Coulomb's law. So let's go ahead and talk about what Coulomb's law represents. Coulomb's law has to do with an attractive force between charged particles. And so we have on the top, the magnitude of the charges, and on the bottom, the distance between the particles. So we are talking about a situation with Coulomb's law where it's either because of a greater charge magnitude that could increase the strength of the attractive force, or because of a smaller distance between the particles. So we actually have both situations in this case. We're talking about a water molecule, and the polar water molecule is attracted to either an iron 2+ ion or an iron 3+ ion. So we actually can talk about both charge and distance and get the correct answer to this question. You only had to mention one of them to get the point on this particular question. So you could have talked about the greater charge magnitude of the iron, the +3, or you could have talked about the smaller ionic radius, which brings the ion closer to the water molecule. So either of those would have been acceptable. So before we get started, I'll just go ahead and show you the scoring guidelines for this particular question from the 2018 AP Chemistry exam. So there was the official answer to part A, either the long form or the noble gas abbreviated form of the electron configuration. In part B, talking about greater electron-electron repulsion for the Fe2+, leading to a larger radius. And then either mentioning the higher magnitude of charge or the smaller size. Note, you did not actually have to explicitly state Coulomb's law in order to earn the point for that question. All right, so now let's move into our lesson. So what you need to know today has to do with electronegativity, and that is a periodic trend along with things like ionization energy and atomic and ionic radii. So what do we know on the periodic table with respect to electronegativity? Well, we know that since atomic radius decreases from left to right, electronegativity values generally increase from left to right across a period, and they generally decrease from top to bottom down a group. Here are some electronegativity values of selected elements on the periodic table, and you can see that that general trend holds true, increasing left to right, and generally decreasing or perhaps remaining about the same as you go down. So, how do we tell whether a bond is polar or nonpolar? We have symbols X and Y that represent two different elements. So here we have two different elements. I'm going to go ahead and classify this bond as polar. I don't have to know what the electronegativity values are to decide that this is a polar bond. I have two atoms and they're different. So they have a different electronegativity, which means a different pull on the electrons that are being shared. So therefore, if I have two atoms and they are the same, that is a nonpolar bond. Now the AP exam is going to ask you sometimes to compare the polarity of the bonds, and we'll talk about that as well. All right, the symbols X and Y represent two different elements. Which of these polar bonds has been labeled correctly? We have a partial positive charge. There's a little lowercase delta, delta plus, and we have a partial negative charge. Now, at this point, without knowing what the identity of the atoms are, it's kind of hard to say which of these bonds has been labeled correctly. So let's go ahead and give you some examples here. Suppose that we have, let's say, phosphorus, and it's bonded to chlorine. Now, phosphorus and chlorine are in the same period, and since chlorine is further to the right in the periodic table, that would mean that chlorine is, in fact, more electronegative than phosphorus, and that would be a partial negative charge on the chlorine. Suppose, for example, we had a oxygen bonded to a carbon. Well, on the periodic table, since oxygen is further to the right, that's more electronegative, this would also be correct. So you'd have to know on the periodic table in general what the trends are for electronegativity to decide which atom has a partial negative charge. Okay, so as I said, in a polar covalent bond, the atom that has the greater electronegativity value will have a partial negative charge. And you don't have to know those values per se, just know the general trend. All right, in a polar covalent bond, the greater the difference in electronegativity, the more polar the bond is. So for example, if I gave you, let's say, boron bonded to nitrogen, and let's say boron bonded to fluorine, you could decide that of the two bonds, the boron-fluorine bond would be more polar because of a greater difference in electronegativity, not because you had those numbers in front of you, but simply because they were farther apart from each other on the periodic table. There'd be a greater difference. So the BF, the boron-fluorine bond, would be more polar. Now, this next slide has to do with a general thing that most students learn with respect to bonding, that for a typical binary compound that contains two elements, the metal and the nonmetal, when they bond together, they tend to form an ionic bond, and that when two nonmetals bond together, they form a covalent bond. Now, of course, there is a continuum between covalent and ionic bonding. If you look hard at a variety of examples of compounds in the world of chemistry, you can find some metal-non-metal combinations that actually have some covalent character, and you can find some extremely polar covalent bonds that sort of border on being, partially ionic. So this is a very simple general rule that can solve some of your problems to decide what kind of bonding is it. But another way to characterize the type of bonding would be to examine the properties. So I'll just give you some examples of properties. Suppose we have a solid that is a good conductor of electricity. Well, what kind of bonding should that solid have? Typically, that would be a metal. So metallic bonding is characterized by solids that are excellent conductors of electricity. So things like copper and aluminum and zinc. If a solid does not conduct electricity as a solid, but can become a conductor when either melted into a liquid or dissolved into water, that's a good characteristic of ionic bonding. So things like sodium bromide or potassium chloride or aluminum nitrate, those would be compounds that, while they don't conduct electricity, when dissolved in water or melted, they do become conductors. Other properties that might give you a clue about the type of bonding: if a solid does not conduct electricity in any phase, solid, liquid, or aqueous, and has a relatively low melting point, so something like water, that would be molecular or covalent molecular. And a solid that has all those properties about not conducting electricity, but actually has a very, very high melting point, that would suggest covalent network. Now, we are right now in topic 2.1, 2.2, 2.3, 2.4. That's in Unit 2. I will tell you that on Friday, we will be talking more in topic 3 about properties of solids and intermolecular forces. So you'll see more discussion of these types of things. I'll move on to metallic bonding, which I mentioned. You should know that at the particle level, a metal consists of a crystal lattice of positive particles. And in that positive particle is the nucleus of the atom and the core electrons. Now, the valence electrons are free to move throughout the lattice. So chemists and teachers and textbooks often refer to this model as a SEA, of delocalized valence electrons. And so that mobility of the valence electrons is why metals are such good conductors of electricity. All right, I mentioned earlier we're going to be talking about this diagram of potential energy versus internuclear distance. So potential energy is on the y-axis, and internuclear distance is on the x-axis. So in this region of the diagram, the potential energy is high, which means that that would be a less stable arrangement of the atoms. And then down here at the bottom of the diagram, the potential energy is low. That would be a more stable arrangement of the atoms. So internuclear distance just literally means the distance between the nuclei of the two atoms. Now, suppose we have these two atoms. As you can see, they are relatively far apart from each other. So the potential energy is essentially zero because there are no attractions between the protons and the electrons, and there's no repulsions either. So these two atoms are not forming a bond. What will happen if we bring them closer together is that the protons of one atom start to become attracted to the electron cloud of the neighboring atom. And so as that becomes a more stable arrangement, there is attraction between the atoms, potential energy is less than zero. Now it keeps moving down along the y-axis until we reach this local minimum. At this point, this is the most stable arrangement for the atoms. There is a balance between attractions and repulsions, and we have a stable bond. So that means that potential energy is at a minimum. This is the most stable arrangement. Along the y-axis, this would be the energy required to break this bond. And along the x-axis, this would be the length of the bond itself. And we'll talk more about this diagram as we take a look at examples of bonds. What happens if we go even closer for these two atoms was that now there's too much repulsion between the nuclei. And this is an unstable arrangement. So as you can see, potential energy is now greater than zero when the atoms are too close together. So a chemical bond is essentially a balance between attraction and repulsions in terms of potential energy. All right, next thing I want to talk about is trends in bond length and bond energy. How are these two properties of a bond related? So we have four bonds, HF, so hydrogen and fluorine, HCl, hydrogen and chlorine, and then HBr, hydrogen and bromine, and finally hydrogen and iodine. Which of these bonds is the shortest and which of these bonds is the longest? Let's review the periodic trend for atomic radius. Well, we know that from left to right across a period, atomic radius tends to decrease because of increasing nuclear charge within that energy level. But when you're going down a column on the periodic table, you are changing to the next occupied energy level, which is going to be farther and farther away from the nucleus. So atomic radius increases. Therefore, fluorine, chlorine, bromine, and iodine, they're all getting larger. So if I were to draw the size of fluorine and then the size of chlorine, I'm going to draw this a little bit larger. And then the size of bromine, a little bit larger than that. And then the size of iodine. Now, I still have my little hydrogen bonded to it. Hopefully you can see that based on your knowledge of periodic trends in atomic radius, that the HI bond would be the longest bond and that the HF bond would be the shortest bond, just based on the fact that fluorine is smaller than iodine. Well, how much energy do you think is required to break these bonds? We're talking about bond length right now. Let's talk about bond energy. Which of these bonds do you think would be the easiest to break, therefore the smallest bond energy? And which bond do you think is the most difficult to break, the largest bond energy? Well, hopefully you can reason through this and think that the longer the bond is, the farther the atoms are apart, the easier it is to break. So HI would have a low value for bond energy relative to HF, which has a high bond energy. Let me go ahead and show you the data. So take a moment to process that data and you can see how bond length and bond energy are inversely related. All right, let's talk about, since we looked at single bonds, let's talk about double and triple bonds. There is something called the bond order, which essentially means how many bonds you have between the atoms here. So we have a bond order of 1 for a single bond, a bond order of 2 for a double bond, and 3 for a triple bond. Which of these bonds, in your opinion, should be the shortest and which is the longest? Well, hopefully you can kind of reason through this for a given pair of atoms of a certain element. So we're not comparing a double bond of carbon with a single bond of chlorine or something like that, but for a given element, as the bond order increases, bond length should decrease and bond energy should increase. So you should be, hopefully, should make sense to you that the triple bond is not only the shortest bond length and the single bond is the longest bond length, but in terms of energy, the triple bond should be the one that's most difficult to break. So it's easiest to break that single bond and more difficult to break the triple bond between carbon. Let me go ahead and show you the data and you can process that. So here we're looking at bond length for carbon, single, double, triple, getting shorter, and bond energy increasing. All right, I want to talk about Coulomb's law again with respect to the attraction, but this time not between an ion and a water molecule, but between ions themselves, between cations and anions in the crystal lattice of an ionic compound. So as we can see in terms of the numerator, which is about charge, and the denominator, which is about the distance between the ions, the greater the charge on the ions, the stronger the attractive force between those ions. And the smaller the ionic radius, the closer we can bring those ions together, the stronger the attractive force will be. And we'll see examples of Coulomb's law in just a moment. Another thing I want to mention, excuse me, about particle diagrams is that we represent particle diagrams for ionic compounds very differently than we do for molecules. With a molecule, you might show an individual oxygen, bonded to a hydrogen like a water molecule, but with respect to ionic solids, the crystal lattice has this big matrix, this big network of oppositely charged ions. And as we'll see on Friday, talking about properties and intermolecular forces, this gives ionic solids unique properties, such as hardness, high melting point. They're very brittle. All right, I want to also mention some particle diagrams for alloys. So we have an interstitial alloy as opposed to a substitutional alloy. What's the difference? Here we're looking at a particle diagram of an interstitial alloy. This is formed between two elements in which there is a significant difference in size between the elements. The atomic radius of one element is much smaller than the other. So the smaller atoms can fill in the interstitial spaces between the larger atoms. Now for a substitutional alloy, because the atomic radius of the elements are roughly the same size, one element simply substitutes for another within the matrix. All right, on to the guided practice portion of today's lesson. We had talked earlier about electronegativity, so now I'm going to give you a chance to put a partial positive and a partial negative charge on the atoms in these three bonds. So here we have carbon bonded to nitrogen. Take a look at your periodic table, and once you find the elements, can you tell me which element is more electronegative based on the position on the periodic table? And that will help you decide who gets a partial negative charge. So if you're looking on your periodic table along with me, you will notice that nitrogen is further to the right. And if nitrogen is more electronegative, it's going to have a partial negative charge. Moving on to our next example of a bond, these are two elements that are located in the same group. So fluorine and bromine are in the same column. They're both halogens. So which element is more electronegative? Well, hopefully you can see that based on the trend we've been talking about with electronegativity, fluorine is more electronegative than bromine and therefore gets the partial negative charge in that bond. Now we have silicon and oxygen next. They are not in the same period or in the same group, but can we still use our understanding of periodic trends and electronegativity to decide which element is more electronegative? So here we see that oxygen is further to the right in the top right corner. So oxygen is more electronegative than silicon and therefore would get the partial negative charge. I want to remind you that the periodic table does give you these trends without the electronegativity numbers given to you. The AP exam would not ask you to compare something like nitrogen, for example, and bromine. So had you been given these two elements, you'd have to be given the electronegativity values because it's difficult to decide based on the trends whether, because bromine is further to the left, but it's also further down the periodic table. So that would not be a fair comparison without electronegativity values. All right, now we're going to be given three bonds, and we have to arrange them in order from least polar to most polar. These are all containing fluorine, and then either nitrogen, phosphorus, or oxygen. You might be asking, would we be given a table of electronegativity values to answer this question? Well, if you were, then certainly you could do the math. But suppose you were not given the actual values. Could you still make this comparison? Let's take a look at these elements. Which element do you think is the least polar? So considering we have fluorine, oxygen, nitrogen, and phosphorus, I would say that the least polar bond has the smallest difference in electronegativity. And so I would go with the ones that are closest to each other on the periodic table. So in this case, the oxygen-fluorine bond should be the least polar. And then as we get farther apart, since phosphorus is not only to the left, but also down one column, phosphorus and fluorine should have the greatest difference in electronegativity. And that puts the nitrogen-fluorine bond in the middle. So you could definitely rank the polarity of these bonds even without electronegativity values just based on trends. All right, as I mentioned earlier, we're going to revisit that diagram of potential energy versus internuclear distance. And we have two bonds, the bond between chlorine atoms and the bond between bromine atoms. We are told that the bond length is 200 picometers and the bond energy is 243 kilojoules per mole for the chlorine-chlorine bond. Now, take a moment to make a prediction about the bromine-bromine bond in terms of bond length and bond energy. So in other words, based on your knowledge of periodic trends, do you think that the bromine-bromine bond would be longer or shorter than 200 picometers? And would the energy required to break the bond be higher or lower than 243 kilojoules per mole. Now, here I have a diagram. This is for the chlorine-chlorine bond. And we can see that this represents the minimum energy, and that would correspond to around 243 kilojoules per mole. We also see along the x-axis, this would be the distance between the nuclei. That's going to be around 200 picometers. So I'm going to go ahead and draw another curve. And this time I'm going to go ahead and make the valley a little bit higher, like that. We definitely have data. We also have our periodic trend. We know that bromine is larger in size than chlorine. So did I do a good job of giving a smaller bond energy? I think that bromine-bromine bond is probably easier to break, but what I did not pay attention to is the x-axis. Let me try this again. What if I drew a curve like this? Well, now I did a good job of looking at the x-axis and making that a longer bond, but I also did not pay attention to the y-axis. This has the same bond energy. So I think what's going on here with respect to the bromine comparison is that it should be a longer bond because bromine is larger than chlorine, and it should be easier to break. So this is the curve that you should have drawn. And if the AP exam asks you a question like this, it's possible they might make this worth 2 points. It might be worth 1 point for shifting the bond length to the right, so it's a longer bond, and you might get a point for showing that the bond energy, that is the depth of that valley or that well in the curve, is smaller as well. All right, I would now like to show you the data. So the bond length is around 228 picometers for bromine, which again is longer. And the bond energy is about 193 kilojoules per mole, so less energy to break the bond. All right, next thing I want to talk about is something called lattice energy. Now, we did see on the screen earlier that you could draw a diagram for a ionic compound that would look something like this. That's in the solid state, but in the gaseous state, they would be completely separated from each other. So the lattice energy is the energy required to break apart or separate the ions in the solid crystal lattice into individual gaseous ions. We are given some data. We're given data for sodium fluoride. It's 930 kilojoules per mole. That's the lattice energy. And I want you to use Coulomb's law to make a prediction about the lattice energy of magnesium oxide and potassium chloride. So do you predict that magnesium oxide's lattice energy will be higher or lower than 930? And will potassium chloride's lattice energy be higher or lower than 930? I'm going to explain each of these on the next few slides. This would be a good moment to pause the video if you want to think about this and make your prediction, and then you can press play to see if your predictions were correct. All right, let's take a look at charge magnitude and distance between the ions. Remember, the greater the charge on the ions, the stronger the attractive force, and therefore the higher the lattice energy. And the smaller the ionic radius, or the distance between the ions, the stronger the attractive force as well. And we are comparing sodium fluoride and magnesium oxide. Let's think about charge and distance. Let's go to our periodic table and find these 4 elements. Now, sodium and magnesium are in the same period, and oxygen and fluorine are in the same period. In terms of size, sodium is a little bit larger than magnesium, and oxygen is a little bit larger than fluorine. So therefore, sodium fluoride and magnesium oxide, there's not a significant difference in terms of size. But as you probably know, with respect to the charge on the ions, we're talking about +1 for sodium, +2 for magnesium, -2 for oxygen, -1 for fluorine. So therefore, if I'm comparing sodium fluoride, which is +1, -1, with magnesium oxide, which is +2, -2, a higher charge magnitude is what's going on here. So In terms of our prediction, since the magnitude of the charge on the ions for magnesium oxide is greater than that of sodium fluoride, the lattice energy of magnesium oxide should be greater. So that's our prediction, greater than 930. Now on to potassium chloride. Well, if you look on the periodic table, sodium and potassium are in the same group, the alkali metals, and fluorine and chlorine are in the same group, the halogens. So we're not talking about a difference in charge. They're both +1 and -1. But as you know, as you go down a column, atomic radius increases because of the increasing energy level of those occupied valence shells. So the potassium and the chloride ions will be located farther away from each other in the crystal lattice. This is not about charge, it's about distance. And since the ionic radii of the ions in potassium chloride are larger than that of sodium fluoride, the distance between the ions is greater, and the lattice energy of potassium chloride should be less than that of sodium fluoride. Now, we've made our predictions. Let's see if our predictions are correct. Lattice energy for magnesium oxide is around 3,800, and for potassium chloride around 720. So yes, our predictions were true. All right, let's talk about metallic and ionic bonding for a moment. Hopefully you can recognize that in this table, copper is a metal, and copper chloride, CuCl2, is an ionic compound. A student checked the conductivity of two different solids, and the results are listed in the table above. Explain why the student got these results in terms of principles of chemical bonding. Now, I added the next sentence because I know in my classroom, sometimes my students will give the following answer. Copper is a conductor of electricity. Why? Because it's a metal. Well, that's not really an explanation of the specific particles and how the behavior of these particles is related to the conductivity of the solid. So you have to go beyond saying it's a metal and that's why it's a good conductor. It's kind of like saying, why is potassium larger in size than sodium? Your answer cannot be because it's located further down on the periodic table. You have to be more specific and talk about what's going on in terms of energy levels and particles and such. All right, so we know that copper is a conductor of electricity and copper chloride is not in solid form. So what I said for copper is the following. You may remember seeing that picture of the SEA, of mobile valence electrons. Copper is a metal and can conduct electricity because the valence electrons are delocalized and able to move freely throughout the crystal lattice. So the sea of mobile electrons is why copper, or any metal, is a good conductor. Now for copper chloride, something is not able to move around. It's not exactly the electrons that are locked in place, but rather the ions, the charges that are the copper ions and the chloride ions. So copper being an ionic compound, in the solid form, the ions in the crystal lattice are unable to move freely within the solid. Again, be specific and talk about what particles are moving or not able to move. Now, if copper chloride is not a conductor of electricity in the solid form, what are two different changes that could be made to the sample of copper chloride that would enable it to become a conductor of electricity? And so the two things that we could do would be to either heat up this copper chloride solid until it melts. So in the molten form, then the ions are able to flow and move and conduct electricity. Or we could take a sample of solid copper chloride and dissolve it into distilled water. And in aqueous solution, now the ions are broken up from that matrix and they're able to flow and move. And a solution of salt water, copper chloride dissolved in water, aqueous, could conduct electricity. All right, next thing I want to mention, I talked about substitutional and interstitial alloys before. Here is some data for copper and zinc. Should we identify brass as an interstitial or a substitutional alloy, justify your answer? Well, since all we really have here is the atomic radius, that should feature prominently in our answer. A substitutional alloy is one in which the atoms of the minor element replace host atoms in the crystal lattice. So substitutional alloys form between metals whose atomic radii are similar in size. So brass is a substitutional alloy because the atomic radii of copper and zinc are similar. Here we have iron and carbon, which are combined to make steel. Should we classify this as substitutional or interstitial? Well, take a look at those atomic radii. They are very different. So an interstitial alloy is formed between atoms of different radii, where the smaller atoms fill in the interstitial spaces between the larger atoms. So steel is a good example of an interstitial alloy because the atomic radii of iron and carbon are quite different. All right, I will now do a quick debrief and summary for this lesson on bonding, and we will then take a look at our homework, which is the AP practice problem for tomorrow. So we looked at types of chemical bonds. We talked about the attractive force within the molecule, so intramolecular, talked about potential energy, looked at the structure of ionic and metallic substances, including alloys. We learned about how to tell if a bond is ionic or covalent, how to tell if a covalent bond is polar or nonpolar, how to compare two polar covalent bonds and decide which one is more polar than the other. Again, we talked about metallic and ionic bonding. We looked at graphs of potential energy versus internuclear distance. We talked about the relationship between bond length and bond energy. We talked about Coulomb's law as it relates to the attractive force between ions in an ionic compound. And then I did mention the definition of interstitial and substitutional alloys and gave you some examples. So now here is your AP exam practice homework for next time. Number 1, answer the following questions about nitrogen and oxygen. In part A, all you're doing is writing the Lewis electron dot structure for the diatomic molecules N2 and O2. Now, we didn't talk about Lewis electron dot structures today, but we will be talking about them tomorrow. And I think these molecules are fairly straightforward for you all to do. In part B of this question, you are given a potential energy as a function of internuclear distance diagram. And these are for the diatomic molecules N2 and O2. So based on the data in the graph and the Lewis structures that you drew in part A, which curve, 1 or 2, is the better representation of the N2, the nitrogen molecule? Justify your answer in terms of the principles of chemical bonding and bond energy. There's also a part 2 for the practice for homework. Answer the following questions related to magnesium and strontium. Part A, write the complete ground state electron configuration for the ions Mg2+ and Sr2+. Part B, do you predict that the ionic radius of Sr2+ is larger or smaller in size than the ionic radius of magnesium 2+? Justify your answer in terms of atomic structure and the electron configuration of each ion. And then finally, part C, the lattice energy of magnesium chloride, MgCl2, is 2,300 kilojoules per mole. Make a prediction about strontium chloride. Do you predict that the lattice energy of SrCl2 should be less than or greater than 2,300 kilojoules per mole? Justify your answer in terms of Coulomb's law. All right, as this virtual lesson comes to a close, I want to remind you about there should be a link in the video description where you can see a variety of helpful chemistry resources that relate to online learning of chemistry. Again, this has been Michael Faribaugh from Albemarle High School. I want to say thanks for watching this lesson. Remind you to go to cb.org/tech if you or anyone you know has some needs for mobile tools or connectivity for the online AP chemistry exam. All right, that's the end of this lesson. Tomorrow we'll talk more about Unit 2. Thanks for watching.